So hope you still remember what we were discussing before the break. Okay, so what we did was this, right? We introduced momentum, the impulse. These two new concepts, both of them are vectors. Okay, so this is the definition for them. The reason we introduced them is because they're very useful in collisions, right? We did a problem last time before the break, right? From lecture 13. Now we're on lecture 13. From slide 5 to slide 7, and also 8, right? So what we did was that we took a collision. We calculate the kinetic energy of these two objects, these two cars, before the collision and after the collision, right? And then obviously they're not going to be equal, right? Because during the collision there are many forms of energy produced. Right? If you only calculate kinetic energy before and after the collision, you don't get the same number. But the total energy is still conserved, right? If you ask me, is the total energy still conserved in this process? Yes, energy is always conserved anywhere, right? We haven't found any evidence against that law, okay? But it's because there are many forms of energy involved produced in a collision. So it's very hard to make predictions using conservation of energy, even though energy is still conserved, right? But if you use conservation of momentum, right? What is conservation of momentum? Change in momentum in a system equals the impulse from the outside, the sum of the impulses from outside. But for momentum, we don't have different forms of momentum, right? We only have one form of momentum, mass times the velocity, then that's it. So if you want to apply conservation of momentum in a collision, well, it's much easier than conservation of energy, right? So that's why in collisions, when we make predictions, we use momentum instead of energy, okay? So, but still, to make predictions in a real-life collision is still very complicated. So we're just going to take a look at some simplified collisions in this class and practice conservation momentum. How do we apply conservation momentum? First of all, when you see collisions, that's when you use conservation momentum, right, instead of conservation of energy, especially for the collision. Before the collision, after the collision, you can still use kinematic equations or conservation of energy. We're going to see examples like that. But if I'm only interested in the collision itself, I would always use a conservation momentum, right? And then setting up conservation momentum is very much similar to conservation of energy, right? The left-hand side, and the left-hand side is, so actually it's easier to set up than conservation of energy. Why? Because momentum only has one form, right? So if I set up this for the system, I just use this m times v for each object to calculate final minus initial, right? So I only have two terms for each object, and that's it, right? I don't have potential, thermal, all these different kinds of momentum, no. So you always have two terms, final minus initial, for each object, then that's the left-hand side. And the right-hand side, as we explained, usually the time for the collision, it's very, very short, right? Only the collision, not including the time before or after the collision. Only the collision, it's usually very short, in the order of milliseconds. So the impulse, even if you want to calculate the impulse from the outside, okay, it's going to be very small. So in real life, even in real life, you want to calculate the impulse from the outside. It's going to be a very small number. So in this class, we're just going to always assume the right-hand side is 0, okay, which is a valid assumption even in real life. Okay, so that's how we apply conservation momentum in a collision. Now let's take a look at this question, lecture 13, slide 10. So this is the question. Again, still a very special collision, a simplified, well-designed problem for this class. Two identical cars with mass 1,400 kilograms, okay, move towards each other with the same speed, 8 meters per second. Right? After the cars collide, they couple and move together with the speed of. So, okay, it's a collision, so I'm going to use momentum and impulse instead of energy. Now let's set it up. First of all, let's draw it out, right? What is going on? Two identical cars, they're moving toward each other. So, well, in this case, you don't really need the number from the mass, because at the end, when you do the algebra, the mass is going to cancel. So M1, M2, and then they move together, they move toward each other with the same speed, 8 meters per second. Now I want to find the final speed, and then after the collision, this is a very special collision. After the collision, they're going to move together. So they will have the same final velocity, because we're going to only have one equation for conservation of momentum, right? So let's set it up. Setting up this guy, as I said, it's actually easier than setting up conservation of energy, even though this can be new concepts, this can be a new law to a lot of people. So changing momentum, two objects, so I would just do M1 V1F minus M1 V19, right? So this is a change in momentum for the first object. Now do the same thing for the second one. Okay, and then as I said, the right-hand side, it's always 0 in this class. Okay? Now let's see, and then V1F and V2F, they're actually the same in this problem. So I can just replace these two final velocity with one symbol, right? VF. Now you're ready actually to rearrange this equation to find the answer, because you only have one variable or one unknown here, right? M1, M2, they're given. V1F and V19 and V2I, it's given. But remember, velocities, forces, and even momentum is a vector, right? So when you work with vectors, you should be always careful. They have directions. So how do I take into account directions? How do I distinguish directions, left and right, up and down? We use signs, right? If you tell me that they move toward each other, then they're obviously moving in opposite directions, right? So how do I take that into account when I plug numbers in? I would assign them the correct signs so that I will get the right answer, okay? So I want you to assign them the correct signs and put numbers in this equation and find the answer for me, okay? I can't have you use your iClicker, through the internet. So, but again, I would suggest that everyone pause the video. Every time we solve a problem, after I explain how to do this, how to solve the problem, pause the video and then do the algebra yourself, and then we can compare your answer with my answer, okay? You learn more when you do it with me, okay, instead of just watching me for the whole video, okay? All right, so I'm just gonna assume everyone did the work, okay? Pause the video, did the work. Now I'm gonna do the algebra. Now I can combine these two terms, put them together, right? Because they have the same final velocity, so you can factor out this final velocity. And then move these two numbers to the right. These two terms to the right, then they become positive. Now if I want to find VF, I just divide both sides, right, by the coefficient. All right, so now you can plug numbers in, right? Because they have identical mass, so you don't even need to put the mass in. And then these two velocities, okay, which one do you call positive, right? If you still want to call this positive, so this number you plug in is this, and this number you plug in for M2, it's going to be negative because it's moving opposite direction. Now if they have the same mass and these two velocities are opposite numbers, you get a 0 at the top. Then you divide. So you don't even count the denominator. You will get a 0, right? Because you have a 0 at the top. All right. So the right answer is A. Right. So that means if there are two cars identical, the same mass, they move toward each other, they collide, they're gonna actually both stop, right? Because remember, this is our prediction, the final velocity for both of them. Okay, and then I attach the link to a YouTube video. So some crazy people did this experiment, okay? And then they had two cars, identical, accelerated to a certain speed, and then collide. After collision, they both stop, okay? Conservation momentum, all right? So, but don't do this experiment yourself, okay? If you decide to do that, well, make sure you have good insurance and have a seat belt on, okay? So that's how we use conservation momentum to solve a problem in this class, right? Now, conservation momentum is also very useful in a real physics experiment, okay? Because when in a real physics experiment, when you want to identify particles, when you want to measure things, right, you usually can't do that directly. So you have to use a law to help you. So let's take a look at this question so we can see how the laws can help us identify particles or find things we need. After decay, so there's a lot of terms, crazy, scary terms here. Doesn't matter, right? Just treat them as objects. Uranium nucleus, okay, it's an object. Radioactive, okay, good to know. Spontaneously disintegrated into a small fragment that is ejected with the magic speed of dust, and daughter nucleus that recoils with that speed. Okay, we want to find the masses of these two particles after the decay. Okay, so this is what happens, right? So this is a nucleus, uranium. After the decay, it becomes two particles, right? And then these two particles, they're going to go in opposite directions, again, because of conservation momentum, right? Initially, if this guy is at rest, so the total momentum is 0. Now, after the decay, it's still the same system. So if you calculate total momentum, you must have one positive and one negative. They're moving opposite direction. So you add them together, you will get a 0. Then you don't violate conservation momentum, right? They cannot be moving in the same direction because there's no way you can cancel the numbers, right? All right. So M1, let's call the first particle M1. So that guy is moving in this direction, 1.50 times 10 to the 7th meters per second, right? So this guy moves in the other direction. What is the number? 2.56 times 10 to the 5th meters per second, right? All right. So if I want to find, so the decay, it's pretty much like a collision played backwards, right? See that, like this problem, right? These two guys, they come together, then they sort of become one object and stop, right? And then if you play it backwards, pretty much like this, right? Okay, you have one object, it decays, and then becomes two objects moving out the direction. So that's why we also use conservation momentum in decays, explosions, because that's like collisions in reverse, okay? Now, okay, so in this problem, we want to find M1, M2, okay? I'm still gonna set up conservation momentum. So this is how I set it up, right? See that I really like these conservation laws, okay? I like them more than Newton's laws and kinematic theory, kinematic equations, because you always set it up the same way, okay? Then you just need to figure out each term carefully. Now let's see. Do we have enough numbers? Okay, because we want to solve for M1 and M2. If we have all the other numbers, then we're ready. V1F and V2F are these two numbers. Again, because they're moving in opposite directions, you have to assign them correct signs so that you get the numbers right? Because you're working with vectors. So V1F, V2F, not a problem. Put them in with correct signs. Now V1I and V2I, what is the V1I and V2I? Okay, so I guess a lot of people are already saying 0, right? Because initially it's 0. Okay, this guy's not moving at rest and then decays. Okay, so V1I and V2I, that's going to be 0, right? So you don't actually have these two terms. So at the end, you only have these two terms in this equation. But okay, even if I have V1F and V2F, I plug them in, I get one equation, but I have two unknowns. How do I solve one equation for two unknowns? Right? That's not possible. So you need another equation because you're solving for two unknowns. What is the other equation? Think about it, pause it, think about it, okay? Because the problem says now I'm going to tell you the other equation. The uranium nucleus has a mass 238 U. U is the atomic mass, so just a different unit we use for the mass in atomic, subatomic scale. Because if you use kilogram, you get like a very tiny number, right? So it doesn't matter. I'm just going to use that a unit. So this guy is 238 U, right? But this guy is actually, because this uranium nucleus is going to become M1 and M2. So initially, you can just consider as M1 and M2 combined together. So that means M1 plus M2, it's going to be 238 U. So that's going to be our second equation, right? So now you have two equations, two unknowns. You can definitely solve for M1 M2. Right? So again, pause the video, do the algebra, okay? See if you can find the right answer. All right, so I believe everyone did the algebra. Okay, so now I'm going to do that here. So first of all, because V1i, V2i, 0, so I would only have these two terms left. Right, and then how do I solve these two equations for M1 and M2? It's like solving for X and Y, right? What do? Well, you're going to substitute, right? You find the expression for X, say, substitute that into the other equation, then you will get Y first, and then substitute again to find X. So say if I want to find M1 first, so I rearrange this equation to get M2, and then substitute it into that equation, right? So let's do that. So I would get M2 V2F equals negative M1 V1F. Right, move this term to the right. Then M2 is going to be equal to negative M1 V1F divided by V2F. Right, now you can put numbers in. Now you see that you must assign them correct signs, otherwise you always get an extra negative sign, you don't know what to do. Okay, if you still want to call this guy positive, this is a positive number. Now this guy is going to become a negative number. Right? So you put them in that negative, so you will get a negative sign here, but that negative sign is going to cancel this negative sign, right? So everything is going to work out at the end if you get all the signs right. Otherwise, you always, have some extra negative signs. You don't know what to do because there are two masses, right? Masses, they must be positive. Right. So then you would have M1, so that negative sign cancels there, so you would have 1 times 10 to the 7 at the top divided by at the bottom. Right? So this is the expression for M2. Then you can go ahead and plug it into the second equation. So M1 plus this whole expression. Right, you can use a calculator to find that number divided by this equals to 38U. Right, now you see you only have one equation on M1 or X. Right, to solve for M1, you get 4U. Right, so and then you solve for M2, you get 2. Then you plug it back into this equation or this equation, right? Either one you can find M2, okay? So that's how you identify the particles. So the M1 is pretty much going to be a helium, right? Because it has 4U. So that's how we identify particles. So this is an example how we use these laws to help us measure things in a real experiment, because you can't measure things directly, right? For example, if you want to know the mass of the particles, right, in the experiment, first of all, you don't see these particles, right? You can only detect them, and when you detect them, you don't see like a phase on the detector, right? Have you ever seen a picture of proton, a picture of electron? So when I give you a picture, you can tell me, oh, this is a picture for proton, this is a picture for electron. No, they are just particles, right? In that scale, you can't distinguish them, right? And then even if you detect them, you don't detect the particles directly. You detect a track, detect their tracks, okay? So how do I use this information to identify these particles? Okay, I did the experiment. It may have produced many different particles, right? So this is one way, right? You collect some data, you use the data, and then with the law, you can do some math to find out the masses of these particles, and then you can match these numbers with the particles we already know. So okay, so this is a certain particle. This is a okay. So that's how we use these laws in a real physics experiment. Okay. So that's slide. That was slide 11. Now there are tons of applications of conservation of momentum in real life, right? So very classical example people use is the gun. Okay, if you fire a gun, please don't do that. Okay, don't do this experiment. If you have seen that in a movie, right, when the bullet is fired, so you always see the gun recoils, right, moves in the opposite direction, right. So that again is very similar to this because momentum is conserved, right. So initially the system is the gun and the bullet. After the bullet is fired, the bullet is going that way. It doesn't matter what interactions happen between them. So if M1, the bullet goes in this direction, M2, the gun must go in the opposite direction so that the total momentum is conserved. Because you add these two momenta together, one is positive, the other one is negative. You will get a zero, right? If you don't have two M2, like if M2 doesn't move, only M1 moves in that direction, there's no way you can get a zero, right, if you add these two momenta together. So they must be moving out the direction. So that's also true if you have seen like ice skating, right? If these two ice skaters, they initially stay at rest, and then if they push each other, you're going to see them moving up the directions. Again, that's because of, first of all, you can say it's action-reaction forces, and also it's conservation of momentum, right? Initially, the whole system with the two skaters, the momentum is zero. So after they push each other, they're moving up the directions. You add these two momenta together, one positive, one negative, you will get a zero, okay? So that's conservation of momentum. Now we're going to study a very special collision. Why are we interested in that? Because as I said, yes, even if we can use conservation momentum to help us make predictions in collisions, but still in real life, collisions are very complicated, right? There are many unknowns in a collision, many factors, many forms of energy involved. This is very hard to make a precise predictions in real life collision. But there's one type of collision, okay? It's not that common. It's actually very rare in real life, but we can make very precise predictions in that collision, which is called elastic collision. And these collisions, they do happen in atomic and subatomic scale, okay? So that's why they're also very useful in physics, in a real physics experiment. So let's take a look at it. Slide 13. What is an elastic collision and inelastic collision? Well, because we compare the total kinetic energy of two colliding objects before and after the collision. And usually you don't get the same number, right? Because there are other forms of energy produced in the collision. So that's what happens in real life, right? So if you calculate total energy is still conserved. But if you only calculate kinetic energy, no, it's not conserved. You don't get the same number, right? So we call these collisions inelastic collisions because the kinetic energy is not going to be the same, which is very common, right? Which is the collisions we see in real life. Elastic collision is where there's no other form of energy involved. Only kinetic energy is in this process, which is very rare, right? Pretty much you don't really see any elastic collision in your life, okay? But they do happen in atomic and subatomic scales, because in that scale there's no friction, there's no sound, right? There's no heat, right? So there's no other form of energy involved in that scale. So it's going to be truly elastic collision. Only kinetic energy is involved. So you calculate momentum before and after, they're going to be equal. You calculate kinetic energy, and then the total energy will be the kinetic energy, because that's only energy involved. So the kinetic energy, you calculate them, you also get the same number. Okay, so we call that elastic collision. So as I said, truly elastic collision, they only occur in atomic and subatomic scales. But in real life, in microscopic scale, the collisions between two very hot objects where the friction is almost negligible, and these collisions, they're very similar, very close to elastic collision. So we can use the conclusion for elastic collisions to make predictions in these collisions in real life. So that's why we want to study that. For example, the collisions between two pool balls are very, very close to elastic collisions. So you can make predictions, very precise predictions for the collisions between pool balls, okay? So let's see, how do we make predictions in elastic collision? So we can set up these two laws, right? Conservation of energy and conservation of momentum very easily in an elastic collision. So if you set up conservation of energy, because there's only one type of energy involved, kinetic energy, right? So you just set up kinetic energy before and after, set them equal. So that's how you set up a conservation of energy. So, okay, so let's say if there are only two, let's just focus on two objects. They're colliding, it's an elastic collision. So this is how I calculate the final kinetic energy of the system, right? And then it's going to be equal to the initial kinetic energy of the system, right? So that's how you set up conservation of energy, because there's no other form of energy. Now, conservation of momentum, you can always set up conservation of momentum for any collision, right? It doesn't have to be elastic. So this is going to be the final momentum of the system, and it's going to be equal to the initial momentum of the system. Okay? And then you can see that now we have two equations, okay? Two very nice equations. If you have V1I, V2I, and you have M1, M2, you can definitely solve for V1F and V2F, right? Two equations for two unknowns, you can always solve. Well, it's a little bit hard because you have a quadratic equation at the top, but you can still solve that. So we're not going to solve that here. We're just going to go ahead and use the conclusion, okay? So then you don't need to remember these two conclusions, okay? I'm just going to write them down and see how we apply them. So this is going to be the equation. You can also see that on the slide. 2m2 okay, so that's how you predict the final velocity for the first object. Now with 2f, it's going to be m2 minus m1. Okay? So that you see that if you have m1, m2, and also these two initial velocity, you put them in, you can always predict the two final velocities precisely. Okay? So that's what we say if it's an elastic collision, you can make very precise predictions, and that's why we want to study that. So as I said, truly elastic collisions only occur in atomic or subatomic scale, right? But in real life, the collisions between two pool balls are very close to that. So that's why we want to practice these two equations in a pool game. Slide 15. So let's see. In a pool game, the cue ball has velocity 5 meters per second, has a head-on elastic collision. So head-on elastic collision, so first of all, I see elastic collision. Whenever you see elastic collision, don't overthink, don't overcomplicate this problem. Just put numbers into these equations. You don't even need to pick a law and solve the problem, because they have already been derived from these two laws. Well, yes, you should set up conservation of energy and conservation of momentum to solve any elastic collision, but you always solve these two equations the same way. You always get these two solutions. So all we need to do, these two equations, they're going to be given on a test. I don't want you to solve them, because it's a little bit hard to solve them, and it takes some time. If you're interested, you can try that, okay? Then we can just go ahead and use this conclusion, right? Whenever you see elastic collision, these two keywords in a problem, that means I just need to put numbers into these two equations, okay? Now let's do that. So this is M1, all right, this is a cue ball, 5 meters per second, collides with the second ball, okay? I don't know these two masses, but in the pool game, these balls, they are almost identical, right? They have the same mass. So as long as I have that information, I'm just going to call the mass M, right? And at the end, you see that you're just going to divide all the masses. So you don't really need the number. As long as you know the relation between them, then you can find the right answer. Now let's see. I want to find the velocity of these two balls after the collision, right? So that's V1F and V2F. Okay, pause the video, put the numbers in, and see if you can find the two final velocities. All right, so I'm gonna now do the algebra. V1F equals, so now M1 minus M2, okay, so that's gonna be 0, right? Because the M1 and M2, they are the same. So that's gonna be 0. Now the second term is going to be 2m2, but that's just going to be m divided by m plus m. Okay, so that's just going to give me 1, right, times v2i. So that's just going to be equal to v2i. So that's the first velocity we found. v1f equals v2i, and v2i is 0, right? Because this guy doesn't move initially. This is v1i. V2i is 0 at rest. Okay. Now, what about V2F? V2F, it's going to be the first term, 2m, right, m plus m, V1i. The second term, 0, because V2i is 0, right? So you will get 0. Or because M2 minus M1 is going to be 0, right? Okay, so you get a 0. So you actually just, and this is going to be 1, so you actually get V19. So that's going to be the second velocity. Okay, so you see that V1F becomes V2I, V2F becomes V1I. Okay, so they exchange velocities, right? Initially, this guy has 5 meters per second, but after the collision, it's just going to get the velocity from the second one. Initially, this guy, the second guy, has 0, but after the collision, it's just going to get the initial velocity of the first guy. So they exchange velocities. So this is a very special collision. That's why sometimes if you play pool, you will see if well, it has to be a head-on elastic collision between the cue ball and the other ball. Okay, so the other ball at rest, cue ball has a head-on elastic collision. So that means they don't move like this. When they move like this, that's x and y, so you're going to have components. You can still apply conservation of energy and momentum, right? But it's just going to be, you're solving this law, two laws in 2 dimensions, okay? If they have a head-on elastic collision, they always move along the same line, then this is what's going to happen. So the cue ball is actually going to stop. Then the second ball is going to get the velocity of the cue ball and then move in the same direction. Okay, as long as this collision is in along one straight line, so you don't have things like this. Okay, again, you don't see this every day. You don't see, even if you play pool ball, right? If the cue ball hits the second ball on the side, you don't see that because that's not a head-on elastic collision. They're going to be moving like that. But if it's a head-on elastic collision, which is very special, very, very special, they will exchange velocities if these 2 objects have the same mass, right? So that's a conclusion in slide 16. Again, you don't need to memorize these special conclusions, right? They're only true for, not just even true for elastic collision. They're only true for an elastic collision where these 2 objects have the same mass, right? So when you solve you do the algebra, you will always get this. V1F equals V2I, V2F equals V1A, okay? It's a very special conclusion, but this, we can actually set up this experiment to test this prediction, right? Even though this is a very special collision. So I do have these 2, you may have seen this in the lab. I do have these 2 cards here. They're almost identical, have the same mass. And then if I have them collide with each other, they will always exchange velocities. So for example, if I have this guy, I move this guy toward the other guy, this guy is going to stop. And then this guy is going to carry all its velocity and keep moving that direction. Right? And then you can do it the other way, right? You can use this guy to collide with that guy, and then they're going to exchange velocities. Always, okay? And it's not because these 2 guys, they're magic. No, okay? If I change the mass by putting something like on this guy, then they're not going to exchange velocity. You're not going to see this guy stop after the collision, right? We can do that. So this guy actually recoils, okay? So what we just said, what we just figured that it's a very special collision. When M1 and M2 are the same, it's going to be a very interesting collision. They always exchange velocities. Okay. Then why does this guy always recoil if the second object heavier than that? Okay. So that's what we want to see in the next problem, slide 17. Okay. So let's take a look at this question. A proton, so still pretty much like this. Now M1 and M2 are not the same, right? M1 is a proton, okay, and then M2 is an alpha particle, which has a mass 4 times the mass of the proton. So okay, I still don't know these 2 numbers, but that's fine as long as I know the ratio between them. I should be able to cancel the masses, just get a number, okay. Now this guy carries a velocity 3.5 times 10 to the 7th meters per second. This guy is still initially at rest. Now proton is going to collide with alpha particle, elastic collision. Of course, because this is proton in alpha particle, you know, in that scale, owning kinetic energy, right? So we want to find the velocity of the proton and the alpha particle after collision, okay? Elastic collision. Put numbers in these 2 equations, then you can get the right answer. All right? So pause the video, do the math, and see if you can get the right answer. All right, so let's solve it. Now V1, so if this guy is V, so this is V1I, right? And V2I is 0. V1F, it's going to be M1, M2, so I'm just going to use negative 4M1 divided by M1 plus 4M1. Now you see that you don't need M1, right? Because you're just going to get negative 3 divided by 5, right? Times V1I. And the second term, it's going to be 0 because V2I is 0. Okay, so you can put numbers in. You don't even need mass. You just need this number. You will get negative 2.1 10 to the 7th meters per second. Okay. Now you do the same thing for the second object with 2f. Now 2 times m1 divided by m1 plus m2, 4m1. Now still v1i. The second term still 0 because v2i is 0. Now I put numbers in, you will find it's going to be 1.4 times 10 to the 7th meters per second. Okay, let's take a look at these two answers. This guy is negative. What does negative mean? That means it's going to reverse direction after the collision. So it's not going to stop, right? Because they don't have the same mass, right? So after the collision, M1 is going to actually reverse direction, move in the opposite direction. M2 is positive, so that means M2 is going to move in this original direction of M1. Okay? So that's why when you add masses to this guy, then M1 is smaller than M2, which is very similar to this. Then if you let M1 collide with M2, M1 is always going to recoil. Okay, even if you don't have numbers, right? Think about this problem. So if take a look at this equation, if M2 is greater than M1, well, V2I is still 0, right? A special case like this. You put numbers in, you solve for V1F, you will always get M1 minus M2 divided by M1 plus M2 V1I plus 0. If M2 greater than M1, you always get a negative number at the end. You always get a negative number at the end. A negative number means it's going to reverse the direction, right? So, okay, so it doesn't really matter what these two numbers are. As long as M2 is heavier than M1, this is always what you're going to see, right? So even if, now I put like 2 bars only, even if I put 1, this is still going to happen, right? This guy still recoils, right? Because, well, it's this theory, okay? And then these two equations, they have been derived from conservation of energy and conservation of momentum. So it's still the conclusion from these two laws, okay? Because they obey these laws. So that's why they behave this way, okay? So I'm going to stop here for the